Alex, hi, great. Yeah, remember you well, Alex. Yeah, great. So thank you and welcome. And thank you very much for the nice turnout. So my name is Peter. I'm president of the Cybernetics Society, Peter Kavalek. Just to welcome you all here and say thank you to Tom for his talk, for giving us his time with Have We Entered a New Normal? Um, by way of introduction, I was just looking at Tom's bio, PhD in neural computing for signal processing, which he thinks is possibly what AI was called back then. Brunel University, university lecturer, industrial design and engineering, and then 200 grant-funded projects covering a wide range of technologies, but including carbon capture, smart energy grids, and energy efficiency. I think maybe the most important, all of that is great, but maybe the most important thing is to know his Substack, Climate Uncovered. And we uncovered him, or rather, thank you to Meg, who uncovered him there for this talk. So I think it's worth everybody taking a note of that, Climate Uncovered. And can I also say, on behalf of the Cybernetics Society, thank you for joining the meeting. If you're a member of the Society, thank you, thank you. And if you're not, then have a look at cybsoc.org, cybsoc.org, and maybe you would like to join us. We need more of you, and we need, we're confronting the issues and the developments and the thinking every single month and more than every month. So with that, please, Tom, thank you so much. And I'll hand over to you. We can see your screen. And thank you, Peter, for setting up the meeting.
Right. Well, thank you, and thank you very much for having me and giving me this platform. I've got quite a lot of slides to get through, but I've built in a few pause points so we can have a little reflect, a little breather. I can have a sip of tea, and maybe if there's one or two questions, then we can sort of cover them as we go through. I've also uploaded a copy of the slides to my Substack account with the addresses there at the bottom. So if I skip through them too quickly, you can refer to them there or use them in your own presentations or work. That's absolutely fine. It's all about getting the message out at the end of the day. So with that, I'll make a start. So what we're going to cover is how we know that the climate is changing. This is the fundamental bit. We'll look at Earth's energy imbalance, which is the critical aspect of the fact that the Earth is absorbing more energy than it's releasing, and therefore, by default, is warming up and changing. We'll look at feedbacks, control, something called climate sensitivity, the rapidly strengthening El Nino that's forming in the Pacific is creating quite a lot of alarm at the moment. So we'll look at that and look at the implications for the 1.5 and 2 degree Paris targets, what the impacts are likely to look like. And then if we get into sort of uncharted territory, tipping elements, the AMOC is the Atlantic Meridional Overturning Circulation, which also gets quite a lot of press these days. So we'll have a quick look at that. Amazon rainforest and deforestation, some economic impacts. And then hopefully the most important bit for this audience, particularly within the sort of cybernetics and control aspects, is the levers that we have to try and do something about all of this. And there are three basic levers: decarbonisation, carbon dioxide removal, literally sucking it back out of the air, and solar geoengineering. And all of these are controversial in their own way. Net zero has become political. Carbon dioxide removal is sort of fought over and argued about. And solar geoengineering, if you haven't come across that before, you may be horrified about what people are suggesting to do. But at the end of the day, it may well become absolutely necessary. And then finally, we'll answer the question of the talk: is this a new normal, and what will the new normal become? So, first of all, obviously, the Earth's climate system is wonderful. It's a fantastic collection of highly interconnected feedbacks and control loops and tipping elements and all sorts of things that exist across not just the physical side of things, the physics involved with how the atmosphere works, but also chemical and biological systems play very important parts and they all interact together to form this really complex and dynamic climate that has sustained life on this planet for so long. But at the end of the day, looking at all of those is incredibly complicated, and there's a lot of work goes into modeling and trying to understand the impact that one particular aspect has on another and so on. But at the end of the day, there is one particular thing that controls the temperature, and that's something called the Earth's energy imbalance. And it's really quite simple. The Earth has a climate system that's very finely balanced between the amount of energy coming in from the sun and the amount of energy that re-escapes back out into space. And these are finely balanced so that the amount of energy coming in equals the amount of energy going out. And in that case, the climate is lovely and stable. Now, it comes in obviously from the sun, from solar radiation. And then the amount that leaves the system, some of it is reflected. So some of that shortwave solar radiation is reflected off of clouds. Some of it makes it down to the surface and sort of reflected off shiny surfaces on the ground, like ice sheets, like glaciers. But even every surface has a reflective quality. So deserts will reflect more than a forest because they're lighter and so on. So there's quite a lot of this shortwave reflection that makes it back out into space. The other half of it is the long wave radiation. So as a body warms up, it emits radiation in the long wave. It emits infrared. This is Planck radiation. And so anything that's warm from a radiator, anything actually, we're down to minus 273, absolute zero, radiates a certain amount of energy. The warmer it is, the more energy it radiates out. And that's where the greenhouse gases come into effect because they absorb a lot of this energy that's being radiated from the surface and transmit it back down, really sort of retain it within the climate system. So those are the balances, and it creates this energy imbalance where if the EEI, as I'll keep calling it now because it's quicker than Earth's energy imbalance, but if the EEI is greater than zero, that means the Earth system is absorbing energy. And if it's absorbing energy, it warms up. And it really is as simple as that. If the EEI is zero, so the amount leaving the system is the same as the amount arriving, then the system is stable and the climate will remain stable. It won't warm up, it won't cool down. And if the EEI is less than zero, a negative number, then the climate system cools down because more energy is escaping to space than is arriving from the sun. And at the end of the day, climate change and global warming and everything connected to it is related to this equation. Now, fortunately, we can measure it. So for the last 25 plus years, NASA has been running this Ceres mission. It's the Clouds and Earth's Radiant Energy System. It's a data fusion of many different systems. There are lots of satellites, but it's also cross-validated with ocean heat content, with buoys and floats that move around in the ocean, measuring ocean temperature and so on. And it provides a 1 degree by 1 degree resolution of the full top of the atmosphere radiation flux, the amount of energy coming in from the sun, the amount of shortwave being reflected back out, the amount of long wave that's making it out of the atmosphere, and the whole thing can be looked at and balanced and calculated and analyzed and all the wonderful things that scientists can do with it. Now, what's important about this, particularly now, is that because the mission started in 2000, we've now got over a quarter of a century of data. And that means that climatologists in particular that like to look at long-term averages that iron out local variation and weather variations and other natural cycles and so on can start to look at this data and say, yes, no, this is a true picture of what's been going on this century. And this is it. So the graph is the Earth's energy imbalance. Starting at, this is the 36-month rolling average. So it starts at 2003, running up to the very latest data. Now, if you go and grab the slides from the Substack, you'll notice that the data runs to April. And I did promise that this would have the very latest satellite data. And NASA released a new pack of data for May overnight. So I hastily changed the slides this morning for you to see, so that you now have the very, very latest satellite data from Ceres to look at. And it's basically showing this picture. The Earth's energy imbalance isn't just positive, so that confirms warming, but it's increasing. And it seems to be increasing roughly linearly. It's got a bit of noise attached to it and so on, as you might expect, because there's still lots of variation in the system that affects the amount of reflection and so on, how cloudy it is globally, and all those sorts of things. But the basic principle is that in 2000, the Earth's energy imbalance was just over a third of a watt for every meter squared of the Earth's surface. And with the new May data, it's now 1.45 watts for every meter squared of the surface. And that's an increase of over 400% just in the last 25 years. So things are moving fast. Now, before you think, okay, 1.5 watts, what's the big deal? It's per meter squared, and the Earth has a huge number of meters squared. We're talking 510 trillion square meters. And when you multiply that by 1.45 watts, you get the energy equivalent of 12 Hiroshima bomb blasts worth of heat every second being added to the climate system. So I've been talking for 10 minutes or so. So in that 10 minutes, roughly 600 or so atomic bombs worth of heat has been added to the Earth system, and that's carrying on every second of every day, of every week, of every month, and so on. So that's really why we're in this situation and seeing climate change impacts increase so rapidly. Now, climate scientists are quite a conservative lot with a lowercase c, and even they have recognized that this is a worrying phenomenon, and that it's more than just natural variation. And so recently, papers have been published by the great and the good that accept that the energy imbalance has doubled from the first decade of this century to the second decade of this century. But I think if you look at the graph, you can see that it's actually quadrupled. And it shows no sign of stopping anytime soon. Now, what we can then do is take that energy imbalance and look at the energy accumulation. So we integrate the EEI, because the EEI is effectively the rate of energy accumulation. And this graph is now showing that accumulation. You can see the curve that shows that it's accelerating, and that's why warming has now been reported and confirmed to be accelerating. And the amount of energy is just phenomenal. I mean, 355 zettajoules has been accumulated since 2000. A zetta anything is not something you come across in everyday life, so it's a 10 to the 21 joules. And take my word for it, that's a huge amount of energy. Note the acceleration, obviously. EEI is the rate of accumulation, so the warming is obviously accelerating. So where does all of that energy go? The distribution is really quite widespread, and quite surprisingly, only 2% of that energy ends up in the atmosphere, in the air. So all of the weather phenomena, the big storms that are getting bigger, the heat waves, and all of those sorts of stuff, they're only making use of 2% of this accumulating energy that the climate is absorbing. 4% of it, so twice as much as that, goes into melting ice. So the cryosphere, all of the mountain glaciers, the ice caps in Greenland and Antarctica, the permafrost, all of that is melting. All of it is accelerating in its melting. And the reason why is it's taking 4% of this accelerating energy that the Earth is accumulating. The land surfaces absorb 5%, and that's drying out soils and all sorts of things, but slightly more than the melting of ice. But the vast majority, 89% of that energy, is going into the oceans. And of that, 52%, so actually 52% of the total, not just 52% of the ocean uptake, but 52% of the energy that the Earth is absorbing is going into the surface layers of the ocean. The layer down to about 700 meters deep. And that's what's driving marine heat waves. You might have seen in the press that the UK and Europe has been surrounded by a marine heat wave these last few weeks and months. There's one in the Mediterranean. There's a big one off the coast of California, which is some of the cause of the extreme weather that's happening over there. And obviously, we've got an El Nino at the moment, and that's releasing a lot of this pent-up energy that the surface ocean has absorbed over the last few years, releasing it into the atmosphere, which is why we're going to see some interesting times for the next 12 months or so. Now, we can dive even deeper into this EEI because the Ceres mission doesn't just tell us the basic energy imbalance. It measures the short wave and the long wave, but it also tells us how much cloud cover there is, what the cloud proportion is. And so we can actually look at the where the contributions have come between 2000 and the end of 2025 in what's made that energy imbalance jump so much. The first thing is that incoming solar has increased a tiny bit. Now, that's not an increase in solar radiation. It's that over the 25 years, the sun goes through these natural cycles of intensity. And over the 25 years, there's been slightly more of the plus cycle than the negative cycle, but it's heading downwards now. So that will balance out. So if someone tells you that incoming solar radiation is what's driving global warming, no, it's not. It's a natural phenomenon that goes up and down all the time, and it's made a tiny difference to this century's rise. The long wave is interesting. That's long wave clear sky, the fourth little bar across, tiny bit of adding energy to the system, but that's it can be thought of if you look at the graph sort of straight away, you think actually long wave has got nothing to do with the EEI. But what's actually happened is that the Earth's surface has warmed because of the short wave that's reaching it, and therefore it's emitted more energy out into the atmosphere, but the greenhouse gases have trapped them. So what would normally happen in a balance is that if the clear sky, the shortwave radiation goes up, the surface heats up, the long wave increases, and the long wave escaping to space would be larger and start to bring that bar down, and everything would balance out again. That's not happening because of the greenhouse gases. But the shortwave is really quite a scary part of that graph. We're losing a lot of reflectivity in the shortwave. So some of that will be that we're losing sea ice. Some of it will be that we're losing mountain glaciers and snowpack and the like, but not very much of it. The vast majority of that loss is actually loss of cloud and a dimming of cloud. So clouds have actually changed quite a bit over this last 25 years, and that's something that early on scientists were unsure whether a cloud feedback of warming would be positive or negative for warming, whether it would accelerate it or diminish it. But it's now obvious that clouds are changing as the climate warms, and that they're becoming dimmer and less coverage over the Earth's surface. So in other words, the planet is dimming or losing albedo. And albedo is a key element. So albedo has dropped significantly. This is a curve from the Ceres data again of the albedo. In 2003, it was 29.32. So of the incoming sunlight, just less than 30% was reflected back into space before it ever reached the surface. That's now dropped by 2.5% or 2.2% to 28.67. Now that doesn't, those numbers aren't huge. We're not talking about we've lost a quarter of the albedo. If we had, the oceans would be boiling by now. But it's a very significant part of that energy imbalance. Sea ice loss is a big part of it, mountain glaciers and snow and so on, but clouds are the main thing. And this is what's been happening with clouds. As the atmosphere warms, the cloud cover is reducing, even though the water vapor content is increasing. So the amount of water vapor that the atmosphere is holding has actually gone up and is going up quite rapidly. I've got a curve on that coming up that I can show you. But the amount of cloud cover is reducing. And tiny percent difference, 67.58 to 67.28 doesn't sound like a great deal, but given the size of the Earth, that's actually 1.5 million square kilometers of cloud cover on average that used to be there in 2000. There's no longer there now. And that's the land surface area of Mongolia. This isn't a small amount of cloud loss that we're talking about. And to make matters worse, most of the loss is actually over the oceans, and the oceans absorb a huge amount of energy, as we've seen, and they also are very unreflective in their own right. So sunlight hitting the ocean, 90% odd is absorbed into the surface layer of the water. So because a lot of the cloud cover is over oceans, this is accelerating the warming of the oceans and everything that goes with. So there are other drivers of albedo. The brightness of clouds has actually diminished as well. So as well as losing the volume of them, or the surface area of them, they're not as bright as they used to be, which means that they're reflecting less light back into space. And aerosols have become a bit of a poster child, if you like, for why this is happening. We have been reducing, as humanity, we've been reducing our aerosol pollution. So especially with things like sulfur dioxide, we've got scrubbers on the remaining coal-powered power stations and so on that are burning coal. We've also got various clean air legislations and acts and all sorts of things going on around the world. And that's reducing the amount of sulfur dioxide that's in the atmosphere. And sulfur dioxide is really good at making bright clouds because it acts, if you like, as little cloud nucleation sites for the water to precipitate around. And the more aerosols there are, the more little droplets of effectively sulfuric acid, the more smaller and brighter cloud particles you get. So as we're dimming the clouds by reducing the amount of aerosols, that's partly what's driving up the energy imbalance. There's good reasons for sorting out air pollution. The sulfur dioxide we put into the air, as long as other aerosols and so on, roughly kill 8 million people a year. So it's worthwhile reducing them. No one's suggesting that we start polluting the lower atmosphere with aerosols just to sort the warming, but they do have a significant effect. In 2020, the International Maritime Organization cut the amount of sulfur that was allowed in bunker fuel, the fuel that the tankers and cargo ships and stuff burn. And we saw quite a rapid spike in the temperature, particularly the water temperature, along the various trade routes that the ships use in the Pacific and Atlantic. And that's been used, if you like, as a sort of accidental geoengineering experiment to see what the effect of aerosols had been on clouds, comparing them before and after that legislation came in, because it effectively cut air pollution by 80% over the oceans. Plants and plankton also emit a lot of aerosols that form clouds, so either over the oceans or through forests and so on. And so the concurrent ecological collapse that we're driving is reducing that source of cloud brightness as well. So albedo is a big thing, and we'll come to that later on in the talk when we look at solar geoengineering. The greenhouse gas side, the main culprit's obviously carbon dioxide itself, mainly from fossil fuel burning and land use change. The most important thing about carbon dioxide is it's so long-lived in the atmosphere. So we've added a huge amount. In fact, we produce more carbon dioxide as a society than anything else. So if an alien was to come down and land on the planet and look at us and say, okay, what do these people things do? The answer would be, we make carbon dioxide. And as a byproduct, we move about, we mine and play with metals, and we build things with cement. But by weight, the most that we do is carbon dioxide. And over the years, since the Industrial Revolution, we've created and dumped more carbon dioxide in the atmosphere than the entire biomass of the Earth, plants, animals, and everything that we've built. The issue is that it's so long-lived. So it's going to take 100,000 years for the Earth to re-sequester all of that carbon and put it back down into the lithosphere. And that's why it has such an effect. It's because it accumulates. Everything that we put up today will still be there in 1,000 years' time, and so on. Nitrous oxide is the one mainly comes from agriculture, over 90% from agriculture, but there's still some emissions from fossil fuel and biomass burning, sewage treatment, and so on. Very, very powerful, but we've only increased it by 26%. Methane is the other big one. We've increased that by 166% since the Industrial Revolution. Mainly, it comes from agriculture. So this is ruminant livestock. All of the cattle and lamb, um, their digestive system produces methane. And so as they breathe it out, it accumulates in the atmosphere. Natural gas leakages, so from the fossil fuel industry, coal mines that have been closed down but haven't been capped properly, leach methane into the air, and waste management and so on. Although a lot of that, particularly in the UK, in waste management, we've actually got methane burners that generate electricity on most of our landfill sites now. Now, methane is very strong. We've increased it by a huge amount, but it's very short-lived in the atmosphere. So it only lasts about 12 years. And the hope is that when we reach net zero, we'll also reach net zero methane emissions. So that will effectively go away after 12 years. There won't be that methane debt in the atmosphere anymore. But it is produced naturally as well from wetlands, from permafrost melt, and so on. So it'll be interesting to see how that plays out. If we melt the permafrost and that emits a huge amount of methane, then we stop our emissions. There'll still be methane in the atmosphere, still continuing to warm us. But at the moment, it's responsible for about a third of the warming. So it's significant. And it's low-hanging fruit. If you wanted to do something quickly to reduce the greenhouse gas forcing, if you like, on the atmosphere, the amount that it's trapping the long-range radiation, then methane emission reduction would be a good place to start. Now, water vapor comes up quite often. You quite often see this from climate skeptics. We'll be charitable and call them skeptics at this stage, where they say the water vapor is a very powerful greenhouse gas. There's more of it than anything else in the atmosphere, and therefore that's what's causing the warming. Yes, it is a powerful greenhouse gas, but it's a feedback of the existing warming. It's not driving warming in its own right. It can't. And the reason for that is because the Earth is very good at maintaining a stable relative humidity. So the top graph there is the relative humidity since actually 1980. And you can see that's pretty flat. It goes up and down a bit, as you'd expect that with natural variation and so on. But roughly 76.5% relative humidity is the global average that Earth has been sat at for the last 40 years or so. But the specific humidity, the amount of water vapor actually in the atmosphere, as you can see, is rising and accelerating. That's the bottom graph. And that makes it a powerful feedback. So as the greenhouse gases and the albedo drop warm the climate, water vapor increases in the atmosphere to maintain the same relative humidity, and that traps more of that infrared. A quick sort of thought experiment, if you like, just to prove that water isn't the driver of climate change. If you double the amount of carbon dioxide in the atmosphere overnight, the planet will warm, and it will stay warm until that carbon dioxide drops out after thousands, tens of thousands of years. If you double the amount of water vapor in the atmosphere overnight, within a week, it would all have rained out. It would be one hell of a week, and there would be storms like you wouldn't believe, and it would have flash floods and general chaos, but it wouldn't stay there, which means that the warming, any warming that was driven by that, by their short life as a greenhouse gas for a couple of days, would be insignificant. So water vapor is a feedback, not a main driver. On top of the fact that we're pumping more and more gases into the atmosphere, we're losing some of the carbon sinks. So nature has been trying really, really hard to absorb a lot of the carbon dioxide that we put into the atmosphere. In fact, it actually sucks out about half of what we emit. And another thing that you might hear every now and again is, hang on, isn't CO2 plant food? It's supposed to be good. It's great that we're polluting the atmosphere because plants love it. Yes, they do grow more and they sequester slightly more carbon with a richer atmosphere, but The downside is that with the global warming that we're experiencing, we're getting more and more extreme weather, which means droughts, floods, wildfires, and so on. And these largely counteract any of the gains. So the fires that are going off in Canada and so on at the moment are releasing more carbon dioxide into the atmosphere than those trees absorbed last year because there was an increase in the amount of carbon dioxide available to them. So that's not really on a global scale a good thing. Trees also respond to an increase in carbon dioxide by reducing their stomatal openings in the leaves, and much of that is related to the water vapor production. So when it comes to a warming climate, it turns out that photosynthesis might increase, which on the face of it would suggest that carbon dioxide is being absorbed from the atmosphere, but it's not actually going into the woody plant matter, the woody material within the plant, which is actually the store of carbon. And there's been some recent research that shows that in some areas of the world, it's actually 30% less than the models predict if you just draw a straight line for photosynthesis against carbon dioxide. The actual amount of carbon that's being sequestered is 30% less than that linear relationship would suggest. There's also temperature limits for photosynthesis and so on. So despite the fact that we have kind of leveled off on our emissions over the last sort of 5 years or so, the atmospheric concentration continues to go up. The natural sinks, particularly the ocean sink, appears to be flattening. And that's really quite worrying. But there was one study that was published in Weather last year that suggested that natural absorption of CO2 peaked in 2008. And so since then, more and more is being left in the atmosphere and therefore driving more warming and so on. So CO2 is in the driving seat. It's the main thing that controls the temperature of the Earth, and it's been doing it effectively forever. So this top graph is the last 66 million years of Earth history. And in that time, we've had hot house, warm house, cool house, ice house. We're in an ice house at the moment, which is this ice age that's existed for the last 2.5 million years or so. It has glacial periods and interglacial periods. We're in an interglacial period at the moment, a warm period. But the bottom graph is actually plotting the temperature on the y-axis, the global average temperature for those 66 million years against the atmospheric CO2 levels that have been measured from all sorts of different methods. And you can see that there's a very strong logarithmic relationship between the amount of carbon dioxide in the atmosphere and the temperature of the globe. And that runs across that whole 66 million years. Because it's logarithmic, you get the same amount of warming if you increase it from the pre-industrial 278 parts per million to 556 parts per million, which we'll probably reach by the end of this century, as if you increase it from 1,000 to 2,000. So that, if you like, provides a sort of top ceiling for how much warming it's possible for the planet to have. So even if you went to 1,000 parts per million, that would only be the same effect of warming from 2,000 as we're likely to do this century. And that's called climate sensitivity. And it's a number that is hotly debated, or not really debated, but various approaches and experts and climate models and paleoclimate studies and so on are trying to anchor down what this number is. In the last IPCC report, so this is what comes out of the COP meetings and the whole UNFCCC setup, their best estimate is 3, but with a range of about 2.5 to 4.5. But the recent data, and including the Ceres data that I showed you earlier, is pointing very strongly to it being at the top end of that range. And so notable climate scientists like James Hansen and others are suggesting that this is 4.5 degrees. That means that there's a lot more warming in the pipeline. That means that we should have warmed by over 2 degrees by now. And the reason why it takes some time is that the climate system needs time to adjust and where to put this heat and to melt the ice caps and everything else. It's not just a switch that suddenly goes. Now, if we zoom in on that bottom graph, we can plot with, and this is all actual data. There's no modeling on the green line at all. This is what's happened to the carbon dioxide and temperature since 1850. So 1850 is the point that we call pre-industrial. We were nicely in the ice house territory, the warm end of the ice house in an interglacial, and we've dragged the system off to the right. And the two orange lines are the projections, the actually quite conservative projections of where we're heading. So the first one is the older SSP type model, which is the medium emission scenario that the IPCC use to take us to 2100. And the longer line is the new model that's being used for the next set of IPCC reports. That's the medium line. And you can see that it's being dragged way out of anything that the climate has experienced before in the last 66 million years. We're driving it into a new unknown state. Yes, it has been hotter before. That's true. Yes, we've had higher levels of CO2 before, but we've never had this combination before. And the climate system is wildly out of balance and trying to find a new equilibrium. And where that equilibrium ends up being, to a certain extent, is down to us. Can we drag it back horizontally? Will it go slightly upwards as it comes back to the left? Will we end up in a cool house environment, which we haven't seen on this planet for 10, 15 million years, when life was very different? Plants were very different, animals were very different. Oh, and sea level rise was about 10 or 20 meters higher. So if you happen to live in London or any other coastal city, just have a look and see how high your house is above sea level. That's a potential of where the climate system would like to take it. So this sort of thing has happened before. We can look back in the paleo records, and the last big anomaly was 56 million years ago, the PETM. Temperatures rose by 5 to 8% 5 to 8 degrees C in just 5,000 years, but that's 10 times slower than we're driving it today. Emissions were very, very high. The Atlantic Ocean was splitting open and belching CO2 out into the atmosphere, and that's what was warming up the planet. And it was belching it out at a rate of about just over a gigaton of carbon a year. Today, we're belching it out at 11 gigatons of carbon a year. In that particular episode, it took 5,000 years for the effect to take place, but it took 70 to 100,000 years to recover, and that's the kind of recovery time we're looking at in terms of the climate today. So I'm going to pause there. I've just looked at the clock and found that I've wildly gone over time. So unless there are any burning questions, I'll just pause there for a second, take a glass of tea. Just to say that we know the climate is changing. We've got rich environmental data. We've got the satellite data. We know that the Earth energy imbalance is out, and that's warming us. We know what's causing it, and we know that this is unprecedented in geological time. So where we end up is largely unknown. Let's look at some other effects. So there's the El Nino. You'll have seen in the press that a super El Nino is brewing. It brings very strong consequences for floods, droughts, extreme weather, and so on around the world. It also provides temperature jumps. And it used to be that when you had an El Nino year, the temperature would rise a little bit, maybe 0.5 of a degree for the following year, and then it would drop back down again when the subsequent La Nina or neutral stage came along. But with the accelerated warming that we're seeing, the El Ninos are acting as ratchet points. So 2016 was the warmest year on record by a long way. That was smashed in 2024 because there were two El Ninos, one in 15, one in 23. And they're ratcheting up, and we've not recovered the temperature back down to pre-2024 levels. The next event, this one that's happening this year, is going to be quite a whopper. These are some quotes from Mark Roberts on his excellent website, and I'll let you just to sort of quickly look at those. Basically, it's going to be grim. It's El Ninos are lined up with major food production areas around the world, and unfortunately, those food systems have been starved by fertilizer shortages and price hikes, by diesel shortages and price hikes because of the war in Iran. And these are all coming together at one sort of perfect storm, if you like. We know it's going to be bad. It's not really a great time for countries to be cutting their foreign aid budgets, but they seem to be. So we can only wait and see what happens. The reason why people are getting concerned is that the 26 event is looking like a true monster, a real Goliath. And this little graph on the right is the model predictions for how the El Nino is going to play out. And the dotted lines are the peak of the last two El Ninos. So the blue line is the strong event that happened in 2023. That saw 2024 become the hottest year on record by a mile. The very strong event in 2015 saw the tipping point pass for the Antarctic sea ice. That has changed regime and it's not recovered since. This event is going to smash all records according to these models. So my prediction for what's going to happen is that 2026 could actually come in hotter than 2024. 6 months ago, everybody was suggesting that was crazy. That couldn't happen. I did a little bit of modelling and came up with 1.65. James Hansen came up a month later with one at 1.7. It could be. Whatever happens, 2027 will definitely beat 24 and whatever this year ends up being, and it could be as high as 1.8 above pre-industrial. We might even see a month of +2 degrees C, the first month on average when that higher Paris record has been broken. And that's something no one was expecting for decades. Because of that ratchet effect, 28 to 30 will be more than 1.6. And so I'm fairly confidently suggesting that 2025, last year, that lovely cool year, do you remember it? Was the last year ever when temperatures were below 1.5 above pre-industrial. And I say ever, obviously in 10,000 years or so, it might drop down, but as far as you and I are concerned, ever is ever. So does that mean we've crossed 1.5? My short answer is yes. Climate scientists like to use 20-year averages, and that sort of grey block there is saying, okay, for the last 20 years, it's been 1.12. But look at the curve. The 20-year average where it is above 1.5 will center probably on 25 or 26. And if we carry on this curve, the 2-degree Paris limit will be second half of next decade, 10 years time or so. And the reason why it's likely to do that is because there's nothing in the Earth energy imbalance things that I showed you. There's nothing in the emissions trajectories or countries' pledges or international policy to suggest that anything is going to change. So we are likely to be in this predicament unless we take charge and really start to take this matter seriously. Quick note, I'll just skip through this really, really quickly because I'm conscious that I am running short of time. But this sort of we must look at the last 20 years to see what the average is. If you applied that to a man in a bath, you'd kill him. I'll let you look at that from the slides on Substack if you wish. So why does that matter? A lot of text on here. I'm not going to read it all out, but it matters because 1.5 in particular has become this sort of standard by which international law is being set. So the ICJ last year and others really sort of enshrined that to say that 1.5 threshold is the objective standard and that all nations have a due diligence obligation to avoid it, to stick to it. And it becomes a law of state responsibility if it's triggered. And that means that damages can be treated as an international wrongful act. And there is a binding duty under international law for countries to avoid this. And even if you've pulled out of the Paris Agreement, like the US has done twice and is out at the moment, that in no way in international law absolves them from that responsibility. They still have a legal obligation to do it. And so the reason why saying we've passed 1.5 is important is because that becomes the trigger for all of these international laws to take effect, and that cascades down into domestic law sorts, corporate liability, human rights cases, and so on. So it's not just a sort of theoretical have we or haven't we, who really cares. This has significant meanings for international law. There are economic implications for rising temperatures as well. Now, earlier on, and so sort of a decade ago, people were thinking that, yeah, okay, so as the climate warms, it will affect GDP, but it won't affect it more than growth. So the economy will carry on growing. And it didn't really dawn on them that although people were saying that, hang on, if we get to 4 degrees C, that's incompatible with our current civilization. It just doesn't work at 4 degrees C. Agriculture collapses, billions die of famine and so on. But it's okay because GDP will carry on growing. That's no longer thought to be the case. And the main people behind this are the Institute and Faculty of Actuaries in the UK, working with University of Exeter people. And they've realized that actually damage follows a sigmoid or an S curve. So total damage is achieved at a top temperature, 4 or 5 degrees C, and it follows an S curve to get there. Now, what that means is that if we take our current rate of temperature rise and our current rate of acceleration, we hit these GDP damage functions really quite quickly. So the green line at the bottom is the highly ambitious, older IPCC scenario, the low emission pathway, which they have now abandoned because we haven't met the first 10 years of it. But that avoids economic meltdown. The yellow line is what happens if the Earth energy imbalance suddenly stops growing, and so the temperature rise becomes linear. Whether you think that's likely or not. The red line, the scary line, is what happens if the Earth's energy imbalance carries on at its current linear growth rate and warming carries on accelerating at the current rate. And you can see that we lose half GDP in the second half of this century. And that's essentially what the Institute and Faculty of Actuaries are warning about in the reports. So if you haven't come across those, I'd strongly suggest you look them up. They're very readable. They're written in a very friendly way. Yeah, if you want to be scared to death, then give those a read for a bedtime story. Next, we get into tipping points. I'm sure most of you have come across tipping points before. It's any system that has 2 or more stable states where there's some sort of hysteresis between the two. So the classic example is a chair. It's stable in the upright position. You can push it back a bit and it will return to the upright position. But there's a critical point, a tipping point, where if you push it just a tiny bit further, it will accelerate down into an alternative state, lying flat on your back, looking a bit embarrassed because everyone's wondering what you're playing at. And it's very difficult to get the chair back again. It takes just as much effort to get it back. Now, the climate system has a number of these tipping elements as well. They're all quite well defined. There are some that are in the danger zone at the moment. So the Greenland sheet, West Antarctic ice sheet. Tropical coral reefs, unfortunately, have been declared to be past their tipping point. They have, they've now had it, effectively. Northern permafrost abrupt thaw, so this is the Siberian permafrost, Canadian permafrost, and the Labrador Sea Current, which is part of the really complicated North Atlantic overturning current. I'll just dwell a tiny bit on the ice sheets because they're really quite interesting. From an ice sheet perspective, if you look at Greenland, the tipping point is actually related to altitude. So the ice cap is about 3 kilometers above the surface. That's the thickness of the ice. As it melts, it lowers down into the atmosphere. And as you lower down into the atmosphere, it warms up. And as it warms up, it melts more. And so it falls down even further, and therefore it melts even faster, and so on. And there's a tipping point, a point of no return, where the altitude of the ice reaches a point where even with no more warming, if we were able to hold temperatures where they were, it's still going to carry on collapsing. And that's really worrying from an Arctic perspective. The Arctic is warming 3 times faster than the global average. It's the sea ice is melting, the permafrost is melting. The Arctic is in real trouble. But the Greenland ice sheet is quite an interesting mechanic, especially if you compare it with what's happening in the West Antarctic ice sheet. And from down there, it's actually melting from the underneath. So warm water, remember the oceans are absorbing 89% of that energy imbalance. And the warm water is it's getting underneath the ice and melting it from beneath and detaching the ice shelves that stretch out over the sea from the ground and forming, enabling the ice glaciers and so on to rush off and so on. So lots of other tipping points there. They've all been very well documented and looked at. But you can see that in 2040, a lot of those danger ones will be more than likely past. 2050, 2.5 degrees C, following that acceleration model, then we're really starting to get into some deep trouble. And these tipping points need to be seriously avoided. The AMOC, I'll probably skip through this quite quickly, conscious of time. But if you want to bring it back up again in the chat, we can get into it. It's really why Northern Europe is so much warmer than it deserves to be for its latitude. A lot of warm water is drawn up from the equator and from the south, and it comes up to the North Atlantic, where it loses a lot of heat through wind transfer across to the atmosphere, and it also evaporates moisture into the air, which provides all of the nice rain that keeps our crops irrigated and gives us something to talk about in the UK. And as it becomes more dense, because it's lost its temperature and it's become more salty, it sinks down into the abyss and flows south. And that is a tipping point as well. It's quite a complicated one because the Labrador Basin that you see on the left-hand side of that map, that's likely to pass its tipping point before the rest of it. That could easily pass its tipping point in the next decade, and that will reduce the amount of warm water coming up from the south. And if the whole lot switches off, then things really start to get tricky. These are models of computer models of the AMOC tipping, and the little pale blue is the line of observed trend. Now, one of the difficulties is it's a very noisy signal because it's complicated by storms and all sorts of natural variations and variability and so on. And we've only been collecting data with actual sensors since about 2004. So although it shows that there is a declining trend, it's a little too soon to be sure as to what's going on. And so the risks are incredibly high, but the confidence or the variability as to whether it's going to tip and collapse is still quite weak. It's quite hotly researched. The reason why it's so important is if we lose that source of heat, that's where sea ice could get to after a complete collapse. Now, complete collapse will take 50 to 100 years. It might happen the second half of the century, which means we're looking at sort of 2150 to 2200 for this to take effect. But weather in the UK over winter could be minus 20 degrees C colder than winters are today. And if you think about what that means for our infrastructure, if you take any one thing, so all cars would have to have snow tires and studs in the winter. Okay, that's not too tricky, but what does that do to our road surfaces? Every road surface of motorways, A roads, B roads, the country lanes, everything would have to be resurfaced to cope with snow plows and studded tires. We might have to bury a huge amount of water supply and sewage because they're too close to the surface and would freeze solid in the winter. Just those two things would be a monumental task to try and undertake. So that's why when people say spending money to reduce the risks of climate change is far, far more economic than dealing with the consequences, it's these type of things that start to really make that take effect. Not to mention that UK agriculture would effectively be wiped out completely if the AMOC were to collapse. Amazon deforestation, similar situation, but made worse by other actions. So this is quite interesting that compares or adds the climate crisis with the ecological crisis, the nature crisis that's going on. So studies show that the Amazon tips to become a savanna rather than a rainforest at about 4 degrees C of global warming. But when you add deforestation, that temperature drops considerably. So a study this year by the Potsdam Institute showed that if you deforest the Amazon by 22 to 28%, that critical temperature drops to 1.5 to 1.9, all the way down from 4 degrees. And today we've got warming of 1.5 and deforestation is already at 18%. That puts the Amazon in a very precarious situation. Tipping points don't just exist on their own. They affect each other. They can cascade. The AMOC seems to sit quite squarely in the middle of them because it's such a large influence on climate, particularly in Northern Europe. But it also positions the monsoon rain belts around the tropics. So an AMOC collapse could have a monsoonal collapse in India. So famine, food shortages, and so on. Greenland melts, freshens the water, which stops the AMOC from becoming the warm water, the colder water, sorry, from becoming dense enough to sink. So you melt Greenland fast, you stop the AMOC, and all sorts of other effects are linked in and so on. So that's sort of hints at the complexity of the system. Quick pause for another summary. So just to recap, we've got an El Nino coming up, which is likely to be or forecast to be the strongest event ever recorded, and that's going to have some devastating effects. It's not just going to be the global south that are going to suffer. We're going to suffer as well through food price spikes, even food availability, cost of living, all of those things made worse by geopolitics. But it is going to be bad. The Paris goal of keeping below 1.5 is blown. That's dead and buried. We could see annual temperatures never below 1.5 again after 2025. Economic consequences are going to be severe, and tipping points only make things worse. There are some positive tipping points, and I'll just mention that if you dig into the work that they're doing at Exeter, there are social tipping points which could help us. So if you like, the adoption of EVs is a good tipping point to look at. It reaches a critical mass whereby nobody in their right mind buys an internal combustion engine car. Why would you? And that's a sort of social tipping point. And there are lots of others involved with how society sort of suddenly takes effect and institutes change. So I encourage you to dig into that if you're interested in the social side of things. Okay, last stretch. So what can we do about it? So we know the problem. We know it's serious. We know there's not much time left. What are the levers that we've got that would actually make a difference? And this little graph on the right is quite interesting. It's known as a napkin diagram because it came out of a discussion over lunch at a conference. But if we don't do anything at all, we follow the red line. So temperatures carry on rising, and all of the bad things that we've just looked at happen. If we reduce our emissions and get down to net zero, then we follow that purple line. So net zero won't return a nice 1970s climate. That's gone. But it would stop it from getting any worse. So the sooner we get to net zero, the better the long-term outcome is going to be. The next thing is carbon dioxide removal, which is that pale blue line, which says that if we can literally pump the carbon dioxide out of the air, if we can do it, there's a variety of ways. We could we could grow crops for burning in power stations, but capture the CO2 and bury it underground, sequester it permanently. That's called bioenergy with carbon capture and storage. Or we can do direct air capture where we literally suck it out of the air with massive fans. You might have seen things in Iceland that are trialing this. And if you can bring the atmospheric concentration down to 350, as been suggested by the IPCC, so that's roughly 1990 levels, then that would follow that blue line of actually bringing the temperature down, because that would have the effect of pushing the Earth's energy imbalance much, much lower, possibly even into the cooling negative zone. The other thing we could do is solar radiation modification or solar geoengineering, and that's the solid blue line. And that's saying that we could remember that the albedo drop is causing a lot of that Earth energy imbalance. If we could somehow reflect more sunlight back into space, we could bring the Earth's energy imbalance down. We could even bring it down to the point where we get no more warming than when we start. So if we did it this year, we could clamp warming at 1.5 degrees. There are all sorts of issues with that, and I'll get into that in a second, but those are the three levers that we have. We can reduce our emissions down to net zero. We can remove the carbon dioxide that we've pumped into the atmosphere and bury it safely, or we could mess around with the radiation that's coming in from the sun. So the decarbonisation side works on the long wave side of that Earth energy imbalance ladder. So net zero would stop it getting worse. Now, the earlier diagram on the last page showed it kind of leveling off quite quickly. But what net zero would do, if you look at this ladder, is it would allow the Earth's surface to warm up to such an extent that so much long wave was getting out that it balanced the other side of the equation. It made up for all of the shortwave stuff, the extra shortwave that's coming in. And that means that warming would continue probably for quite a while before it stabilized, but it would eventually stabilize. There was a recent study that showed that actually the Earth energy imbalance would carry on rising for about 15 to 20 years after net zero was reached, and not actually return to zero for about 100 years. It's quite an early study. It was done by Reading and I think it's the Dutch Meteorological Office. But it's a peer-reviewed study. It's out there, and it kind of makes sense when you look at this diagram that it will take a while for the long wave to get strong enough to be able to escape the amount of greenhouse gases. So that's net zero. It only stops the additional human greenhouse gases as well. It doesn't stop natural emissions and permafrost and so on. So all of the natural feedbacks would continue. When it comes to decarbonisation, though, carbon dioxide removal is the only way of permanently bringing that energy imbalance back down and turning it negative to restore cooling if we actually wanted to do any cooling. So the damage has been done. We've been treating the atmosphere as a free waste disposal area, and now we've been told that we need to clean up all the waste that we've been dumping in the atmosphere since about 1990. But it could be done. The solar radiation management approaches, there are a variety of these, and I'll skip through these quite quickly, but if you want to dig in more during questions, we can do. There's surface enhancement, so we could paint all our roofs silver or white to reflect as much sunlight back out into space as possible. If you run the numbers, because the energy that we're talking about is so huge, you'd actually need a line of mirrors all the way around the equator, so land and ocean, 90 kilometers wide in order to reflect the amount of shortwave radiation that we've increased the absorption of since 2000. It's not to say that that's not that surface enhancement isn't a good thing to do, because it does provide brilliant local cooling. So if you're in the tropics and the heat is rising and rising, if you paint the roof white, or even better, put solar panels on it that can drive cooling devices within the house, then you can make your habitat much more survivable. So that's great, but it's not going to do anything for the Earth's energy imbalance as a whole. There's techniques like marine cloud brightening, where, remember, it's a lack of aerosols that is causing a reduction in clouds. So if you spray really, really fine salt particles into the air, you can induce clouds to form. And that's working quite well. They're trialing it in places like the Great Barrier Reef to try and provide some local cooling. Again, you'd need massive amounts of it to try and have a global effect. But for local cooling and protecting particularly vulnerable areas, that could be good. There's stratospheric aerosol injection. So those aerosols that we're cleaning up the troposphere with, the lower atmosphere, if we pumped a load into the stratosphere, sort of 15 kilometers up into the air, that would reflect a lot of sunlight, and that could be something to do. You need a fleet of special planes flying around the clock. You could put mirrors in space that reflect some of the sunlight before it even reaches the planet. And there are proposals for things like a 40-kilometer wide mirror that you could put at the L1 Lagrange point that would reduce the incoming sunlight by about 1%, and that would have that effect. Cirrus clouds, those very high-level clouds, they could be reduced through rerouting planes to avoid them creating contrails, or with chemical inducement, and other sort of marine sky brightening with more aerosols and so on. So if you've not come across this before, just in your mind, think which of these is the most outlandish. Which of these do you think would be the one that you think, oh crikey, they're not thinking of doing that, are they? While you're thinking about that, let's just sort of look at the effect that it has. So all the cloud engineering stuff would increase the shortwave, or sort of, yeah, would increase the shortwave cloudy area albedo. So it would increase the amount of reflection that we get from clouds. The stratospheric aerosol injection and space mirrors would work across the whole shortwave reflection. Now, one of the things that's really important about this, all of these techniques, when it comes to solar radiation modification, they only work as long as they're continued. So if we were to do, say, stratospheric aerosol injection and cool the planet that way, or at least stop it from warming, we'd have to carry out carbon removal at the same time, because otherwise that carbon is still accumulating in the atmosphere. And when, for whatever reason, you turned off that aerosol injection program, you would jump within a year to whatever the temperature would have been if you hadn't been doing it. That's called termination shock, and it's one of the big concerns with this type of engineering. So if you did it for 20 years and then abandoned it, you get 20 years worth of warming in a year or so. So it's part of a package, and this is really part of these three levers. And really, we have to do all three. We have to reduce our emissions, we have to lose the carbon, and we may have to do some solar geoengineering in order to avoid some tipping points, like an AMOC collapse, for example. As you can imagine, and I'm hoping that you might have thought, actually flying and dumping 10 million tons a year of sulfuric acid into the stratosphere is one of the most outlandish things that you've ever heard of, if you've not come across it before. But this is the leading contender. There's a growing level of support and funding for it. The UK ARIA is funding about 60 million into planet cooling, and some of that is going into SAI. And it's fair to say there's a lively debate. So on the advocate side, the scientists involved there accept that there are risks. There's risks in everything. It could change rainfall patterns. There's this termination shock risk, but the risks of not doing it far outweigh the risks of doing it. So in other words, carrying on with this accelerating energy accumulation, risking going through tipping points, risking the Arctic collapsing and permafrost setting off a bomb of methane that would make the warming unstoppable, is worse than the risks of actually doing this. On the other side, very many notable scientists are very concerned about it. This is a quote from a paper last year by a group of polar scientists, and you'd think that they would be more concerned about protecting the Arctic, but they are very against doing anything like this. Mainly, it has to be said through a sort of moral hazard argument, in that if you tell society it's okay, we can stop the warming by doing this geoengineering, then we'll take our foot off the gas in terms of decarbonising and doing everything else that we need to do. But this is the debate that's actually happening. On some of the plus sides is that the effects wear off after a year. Everything just rains out after that. So if you started it and it turned out that there were side effects that you didn't like, and the world decided, no, this isn't going to work, we're going to have to do something else, then it could be stopped and the effects would wear off really quite quickly. But on the other hand, if you carried it on and it did work, you would need to carry it out until you'd reached net zero and your carbon dioxide reduction had successfully brought concentrations back down. And that could take centuries. So you're locking in every future generation into this practice, and that leads to that moral hazard. And goes without saying that regulating this and international law implications are complex. So, getting to the end now. So, is this a new normal? So, I would say the old normal is gone and we can't get it back. If you remember the 1970s and the weather was like then that's good for you, but you're never going to see it again, and neither of any of your descendants. There is no new normal yet, though. We're just at the beginning of the fastest change the planet has ever known. The energy imbalance is increasing, and that's accelerating all of the changes that I've talked about. And so, no, we won't find a new normal until all of that is brought down. All the measurements are accelerating. We know that. There is no new stable normal until we stop polluting the planet and destroying the ecosystem. So the longer that takes, the less recognizable the eventual normal will be. Whether we can or should stabilize the planet using SRM is an open question. I think if you were to ask me, I'd say that it should be urgently researched for all the reasons I've gone through. But it should be funded at government levels. We don't really want billionaires doing this on their own. It should be something that everybody has a say in how it's done, and we should certainly not rush into it because that could be disastrous. I'm going to leave you with a question. So as cyberneticists, there are levers available to us. We've got this emissions reduction, carbon removal, solar radiation management. Are they strong enough to be able to cope with that? So thank you for your attention and the opportunity to be here. I realise I have run over time a little bit. I hope that's not too bad. A quick shameless plug for my Substack, where you can find all of the slides that I've gone through and a lot more, and it's free. So thank you very much.
Yeah, thank you, Tom. And no, you've not run over time, because I think some things we need to take time over. So thank you so much for that. And thank you, everybody, for the comments and questions coming through. Just to also invite Peter, if you want to step in at any point and contribute, or Meg, that's great. But meantime, I'll get the kind of discussion going. So many comments coming in, and I've been intrigued by by the different categories of comments. But does anybody want to put up their hand and ask a question live first, if we start that way before we go into the feed? I bet there is.
Wow.
Yeah, go on. Who's that?
James has a physical hand up.
James, yeah. What? Yeah, James. Why don't you go first, James?
Hi. Tom, thank you for that. I thought it was tremendously good systems analysis of what's going on.
Thank you.
I think from a cybernetic point of view, though, there's a number of huge elephants in the room that weren't discussed in terms of levers and mitigations, and an awful lot of things that weren't discussed, obviously, because of your remit, that are additional provocations on the destruction of the planet. Yeah. So overfishing, over farming, water courses, you name it, just to add to the total depression. But the biggest elephant in the room for me is population and behavior, because it's human behavior which is driving all of this. Population growth has, well, it's gone up eightfold since I think it was 1850 or whatever it was. I mean, we're now 8 billion, we were 1. And it's kind of inescapable that, one, it's not just obviously population, but it's the whole of the world's population trying to be post-industrial or coming up to a post-industrial standard of living. And we're obviously ahead of that curve because we've kind of gone through it. And if the rest of, I mean, if you look at the emissions, you said at one stage said that emissions were kind of tailoring off, but they don't seem to be from the numbers sort of on the world global charts. And China's the one that's really producing loads of stuff because they're producing stuff for everybody. So unless we stop consumption and unless we, well, potentially reduce population, we're all just dealing with the symptoms rather than addressing the causes.
That's certainly true. I think some of the latest data I've seen suggests that population will peak somewhere potentially around 2060.
Yeah,
it's not going to go much further, and it's also growing in the global south, but shrinking in the Western economies. And it's the Western economies that are doing all of the damage. But you're absolutely right that there's that sort of aspiration of the global south to consume and be as wasteful as we are.
But just to hold you on that, but it's the population growth and the industrialization of India and China.
Yeah.
If looking at the numbers,
yeah,
and we're outsourcing to them to produce stuff for us, but that's what's driving it. And even though the population growth tails off, it's a bit like carbon emissions tailing off. It's about the absorption. If all of those people now want to have the same lifestyle as you and I, and you could say, well, why shouldn't they? They can't all have fridges and air conditioners and houses, because there isn't enough resources to actually create it and have a world that isn't killing everybody off.
Right. So there's a couple of things that are sort of hopeful in that China's emissions do seem now to have plateaued. And that's from the carbon budget reports from the end of last year. They've also, it'd be interesting to see how the Iran situation plays out, but their oil consumption has dropped considerably this year. So their emissions are plateauing.
But they are burning more coal. They are
burning more coal. That's true. There's also the opportunity that some societies could leapfrog the technology space that we went through. So if you take sort of places in sub-Saharan Africa where they didn't have telephones, they didn't go through the copper stage like we did. They jumped straight to cellular. So there is a leapfrog opportunity, and Africa is actually importing massive amounts of solar panels and electrifying things. In fact, some of the fastest growing EV market shares are in Africa, so there is that sort of hope, if you like. Renewables are growing, but they're not yet replacing fossil fuels, but they are largely absorbing the growth in demand. We could get into what AI data centers might do to that, and what Europeans dashing for air conditioning might do for that. But you're absolutely right. The situation is interesting.
The lever we could potentially pull is letting go of this concept of infinite economic growth.
Yeah. Yes.
Yeah. Can I just say something? Sorry. Just relevant to the question. Very interesting. You mentioned population, but I think as systems theorists, I think we have to think about that's sort of the substrate. That's the aggregate. If we look at, we have enough food for everyone right now. We could feed everyone in the entire world right now. Huge amounts of it is wasted because our systems currently do not work in such a way that facilitate kind of global distribution of these things. So a lot of this is actually the fact if we design better systems to distribute these things and as you're saying, increasing the profit margins become such that it dominates everything. If we made better systems, we could actually, we wouldn't have a population issue. It's a logistics issue, maybe just a bit of that, you know,
Yeah.
as a systems theorist.
That makes sense. Yeah.
Yeah, thank you, Rowan. That's very helpful. I'll keep going with the hands in the air. So I'll go to Bill next. And after Bill will be Mike. I'll just go along that list for a little while and then we can have a look at the chat. So Bill, to you, or have you gone? Yeah.
Good evening. Good evening.
Yeah,
I have done a website, Climate Change Info, and what's happened in the last 4 years is staggering on the rise of the heat. We have to remember the problems the incumbents have proposed. The horse people oppose the car. So you have to walk in front of a car. Are people aware of how much the oil companies are spending on disinformation and opposing? It's absolutely incredible. However, the technology is moving so fast. In the last 20 months, we've gone from 2,000 gigawatts of solar to 3,000. And in 2 years, Pakistan has doubled their energy with solar. And batteries are dropped in price dramatically. So, and electric cars, I mean, BYD in China are building a car factory 13 miles square miles. So things are moving fast. But what we need is the will over the whole world to change. And the last thing I'll say, the good news is because of the failure of the COPs, Netherlands and Colombia organized the fossil fuel treaty meeting in Colombia in April with 62 countries, including the UK, saying we have got to phase out fossil fuels. It's been the most amazing breakthrough in hope that will change things and stop these oil companies killing us.
Thank you, Bill.
Absolutely. Yeah.
Tom, if you want to respond, please say.
No, I think that's absolutely right. That's especially the sort of anti-COP or the new group of the coalition of the willing, if you like, getting together and taking the problem on is a brilliant step forward.
Yeah.
Well put, Tom. Mike, thank you, Bill. Mike.
Thank you, Peter. Tom, I really enjoyed the data-rich presentation that you gave us. It's very nice to see all these physical implications arising from different wavelengths and all the rest of it, and deep water pumps and so forth, manifesting to a set of interconnected, interacting feedback loops that so dramatically affect all aspects of our ecosystem and planet. My issue is, I think, a little bit connected to what Bill was just talking about. And it's this: because of my advanced years, I can go back 50 years to a point where all these issues were known by politicians, by industrialists, by economies, by nations, and all the rest of it. In 50 years, when I used to have very, very strong arguments, particularly with the Quaker friends of mine about the introduction of nuclear power, I was a great believer in the fast breeders and the Magnox reactors in those days to sort of take out the carbon elements of burning coal and producing gas from coal through the clinker, through the heating methods that they had back in the day. My question is really to do with, and please forgive me, I come from an absolute ocean of ignorance on this. But since we knew all this, where on earth is the political will through the United Nations and other nation states to actually collaborate on forming international systems that help to resolve this for the next generation, for my kids and my grandchildren and yours? I don't get why we are in a situation where we've got Trump looking to pardon Netanyahu, who's guilty of, etc., etc., and that same thinking will probably apply to those who are guilty of destroying and killing people through the policies they're using to continuously pollute the atmosphere. Have you got any insight into how we can actually organize ourselves internationally so that we can actually collaborate to remediate this?
I personally don't know. I think
I don't either. I'm sorry.
No, but that's not really my area. But if you think back to the Montreal Treaty with the ozone ozone problem and CFCs. That only got so that was known about, and it was researched, and everybody knew what the problem was. And that was equally rebutted and told no, it could never happen until the industry had an alternative. Once the industry that produced the CFCs had an alternative product that they could sell, they then went to their governments and said, it's okay, you can sign that and we'll still help you get re-elected. And so Montreal went through because there was an alternative product. It could be, hopefully, that not in the not too distant future, electrification provides that alternative powered society that means that we can wean ourselves off fossil fuels.
The question then is, how do we produce the volume of electrical power to do that?
Well, I mean, as has already been said, the solar is now the cheapest form of electricity generation ever. Battery prices falling through the floor. You've only got to look at the extent to which Texas, as a state, is installing wind, solar, and batteries to see that the financial argument is strong, regardless of what fossil interests they might have. So, if the economy lasts long enough, if we don't destroy it first, there is an opportunity left.
Thank you. I'll remain optimistic.
That's all we can do.
Thank you, Mike, and thank you, Tom. James, you're next. Thank you.
Yeah, a lot of things. One thing that I love seeing the Archaeopteryx on the wall behind you, Tom. I think it's a great symbol of what we're going through as a transition period, what the Archaeopteryx was from
Well spotted.
dinosaurs to birds. My concern is that all the graphics and the scientific criteria that you filled the first part of your presentation with, that's not where the force really needs to be applied. Somehow the messaging has to be shifted to more prominent to populations themselves, to show them graphically where the cost has been over the last several decades and will continue into the future. The cost of living that goes above inflation, the quality of life that's been diminished for a lot of folks. As far as the question of what happened in the last 50 years, I've always seen it as a long-term thing that after World War II, there was a great transition between the quality of life for nation states beforehand and afterwards. So industrialization has really raised the quality of life for the majority of the population of the world. Been great benefits have been accrued to humanity by all this, the great efforts have been done, even at the degradation of the ecology and the environments and the terrible things that are happening there. So there's benefits there that people have seen that they feel immediately, and they relate to that more than they do to this catastrophe looming that's for their grandchildren and children. But somehow that message needs to be driven home really hard. And I don't know if that's possible, but somehow the details have to be, that would be my recommendation, to shift them somehow to grab the attention of that population.
That's incredibly valid. I think a couple of thoughts spring up from that. One is, and I've noticed someone in the comments mentioned it, in the UK, there's been something called the National Emergency Briefings. It was an event that was held in Westminster Hall with over 100 MPs and peers and so on turned up to look at that. But there are now a whole series of national, or what they call People's Emergency Briefings, springing up all over the UK. And so what I advise everyone to do is to check out nebriefing.org, so all one word, nebriefing.org, and find a national or a People's Emergency Briefing session near you. There's about 2,000 of these have sprung up over the last few months. There's what they did was they took the talks that the national briefing gave, and they had a variety of speakers, scientists from mainly from the UK, in fact, all from the UK, and they covered all of those things. So they covered it from a national security aspect, they covered it from a food security aspect, they covered it from a nature aspect, and so on, and tied everything together. So that would be a brilliant way of getting people involved. So yeah, there've been 2,000 events either happened or booked in. There's a map on that website that shows you where your nearest one is. and yeah, encourage everybody to go along and see what's going on, what's happening.
I think that's great, but I'm really concerned that the message has to go into individual households, not more than
Yes.
the community.
So one of the things that the National Emergency Briefing are trying to do, and you can do that from their website as well, is they're getting a petition going. They've already got over 100 MPs signed up to it, to force the government to have a national televised emergency briefing on all channels to bring the public aware of the situation and talking about it from a food security and national security and health and everything else perspective.
If those groups could also, work towards cloning themselves internationally, that would be outrageous.
Yes, yeah, I think there's they did say, I was looking at the thing to the number of them have happened outside the UK, and they are willing to talk to other countries to see if their scientists would like to get involved, or their experts would like to get involved and spread this wider. But yeah, check that out and see if it's something that it could work.
I'm in the US, but thank you. It's very comforting to hear that. Thank you.
Good.
And thank you again, Tom, for that answer, and thank you, James. I think we go to Benjamin next, and then back to Rowan. So Benjamin next, Rowan, and then we'll have a look at the chat. Thank you.
Thank you, Peter. I really enjoyed this presentation. I think what I enjoyed the most was the tenor of it, and at no point did I feel like I was being presented a straw man argument, and very, very dispassionate. So I would like to add one piece of commentary, a step out on a limb, and kind of amplify Jamie's point. Is that call this a second order perspective? Is that I think as systems thinkers and cyberneticians, and by association scientists, we always have to be mindful that we're not neutral. And even if we are, we have a history that is not. And this goes back to, say, Thomas Malthus. And you could make arguments and go back to the Jacobins and the French Revolution. But to sum it up, I'd say that whenever scientists speak with certainty about anything and then start using the words of force, and we must force people to understand and force people to be virtuous, it brings up memories. And I live in a part of the world that there's a lot of assumptions, a lot of I would say reductionist arguments. We can reduce people to our versions of the reasons we think they're doing what they're doing without asking. So I think perhaps my message would be to always try to keep debate open, because there's less and less of that. And so if you read a lot of the thinkers just from our tradition, it's really important that we keep the debate open, and just maybe as much as possible ask people and inquire into why they believe, and kind of take a Gordon Task perspective of, we may not actually know why people do what they do until we can explain what we think they're why to them, so that they would agree. Yeah. And that's probably enough. So I hope that resonates with somebody.
That's useful. Thank you.
Yeah, I do think that's important, Benjamin. I think that's an important contribution. Thank you for that. And so to Rowan, why don't you come back in now? Thank you.
Actually, thank you, Benjamin. That was brilliant, because that moves very well onto my next point. It's interesting to me that you mentioned the history and sort of the coldness of some of science towards it. And this also connects to Mr. Venon's point, which was about why are we here? We've known about this for decades and decades. And Stafford Beer actually talked about this with his talking about new and adventurous ideas. He talked about basically how institutional inertia occurs, and I'm sort of developing my own theories on that based off of the idea that these institutions, like oil companies, have like homeostatic functioning, which means that essentially we're not facing other humans. We shouldn't be blaming these people. We are facing a system, and what we're at right now is we built systems to serve our purposes as tools. We are becoming the tools of these systems' purposes. And so our job should be towards furthering human capacity over controlling these systems, as opposed to the other way around. That's sort of how I'm looking at it there.
Yeah, no, that makes sense. And I think if you look at there's almost a sort of two system competition going on at the moment, with fundamentally the US, particularly the current administration, which is trying to prop up a carbon economy, competing with the Chinese Asian system, which is trying to develop an electro economy. And the actions that we're seeing play out geopolitically are part of that struggle, which is why you've got the oil companies spending hundreds of millions a year in misinformation and, has to be said, disinformation, because they're desperately trying to prop up the petrodollar at the end of the day.
Fabulous. Thank you. Thank you again, Rowan. And thank you for the answer. Now, so back in the chat, there's kind of different themes we can explore there. There are some questions about measurement and the science. There are also questions, somewhat more philosophical questions, but quite a lot focus on engineering and engineering possible measures and solutions to kind of accompany those raised by yourself. And on the theme of China, maybe I'll pick out Isabel's contribution where she's talking about a huge solar station in space that would be clean energy backwards towards Earth. You come across this initiative, Tom, and what am I to make of it?
Yeah, I don't know much about it. I think if that plays into part of the decarbonising energy production, then that would be something worth looking at. As
but certainly, I take your point about the kind of interesting alignment where we have China and Asian countries taking one position and somewhat contradicting the kind of the way I've been taught to think about the world. The USA taking the kind of retrogressive position. So, yeah, I take that point.
Yeah, there's the space mirror part is sort of interesting to look at from that sort of energy in space perspective. So it kind of relies on us having a moon base where manufacturing happens on the moon, because you can't get that amount of material out of Earth's orbit very easily, which kind of relies on there being an orbital industry sort of in place. And if that part of that involves energy generation and transmission down to Earth, then that could be beneficial. I think I have a slight concern that I'm not convinced that the global economy will still exist long enough to be able to afford a lot of this long-range space-based sort of science fiction stuff in the century to come. But that might be just me being a bit pessimistic.
Yeah, okay, but that's a point noted, and Isabel provided a link in the chat there, so that's interesting. In fact, 2 links. So thank you, Isabel, there for those contributions. Now, next, there were also on the, if I just stay on the engineering theme, then we carry on a little bit more before we kind of go to later in the bar, our segment. So if I, where was I looking? I was just looking at, we had ideas of paint and other things like, so we have.
Yeah, there's a new paint that's being invented.
That's it. Thank you, Meg.
And it reflects infrared. And in the process, you get water for free.
Interesting.
Yeah, I think there's some work done at York University where they were looking at different compounds to make roof tiles out of that reflected as much shortwave, but also emitted longwave infrared efficiently as well, which is, again, I think it's great for the household and for local cooling, very local cooling, but won't do much on the large scale of things because the amount of energy we're talking is huge. As I say, this line of mirrors around the whole of the equator needing to be 90 kilometers wide in order to counteract the drop in albedo since 2000. We're not going to solve it just by painting roofs, but if it's great for the occupants, then that's wonderful.
Yeah,
interesting. Can I just chuck in on this because so my daughter, for example, has tried to they built an off-grid house. Okay, so everything, water, electricity, everything, all recycled. The only thing that they're all solar and everything else. The only thing that they've got which isn't is a bottle-driven gas cooker, right, in the whole thing. Getting planning permission has been opposed for months, well, years actually, based on the fact that where they live, which would be then, or where they will live, which is a mile outside of a town, would necessitate them having a car, right?
Interesting.
And it went, and the politics of the area is green, shall we say? Yeah. And that's their opposition, and they had to take it all the way to appeal to actually be granted the right to have an off-grid house, which is totally environmentally friendly. So down at local level, and obviously it mirrors all the way up, even the small actions that people try to take are obstructed and obfuscated and made difficult. So we just don't have a will. No. You only have to look at what we've done with net zero and what everyone else has done. So
yeah, and I mean it's nonsensical sort of across the board. You're still getting lots and lots of new housing being built on floodplains in the UK.
Yeah.
Even though Flood Re, the reinsurance, doesn't cover any properties newer than 2009. So it's just nuts. Yeah.
Yeah, point taken, and that's a depressing one, James, but necessary. Heiner, I know you were waiting before, so why don't you come in now?
First, I would like to congratulate. It was a presentation I would have loved to include in 1990 when we talked about global change challenges to science and politics. So it's like a déjà vu. When you speak about the three levels and so prominently and so deeply knowing about all these gases, why did we just miss the central points? Like the original draft of the Club of Rome was participatory, normative, and prognostic futures. You're talking here about futures making and futures design and futures creation, like Christakis and Warfield and whomever you want to name. But really step back, not just see the woods, the trees, but the woods. So anyway, your issues raised on that it is not just CO2, and all this are all well taken. It needs more time. I just had a couple of power leaks and breaks and blackouts, so I'm not really prepared, but thank you for the session.
Thank you, I appreciate that. You're welcome.
Yeah, that's very helpful. So just before we go to kind of later in the bar, which is where we go without the recording, I mean, there's so many things that I could be picking up on, but John Jones has come in more than once with kind of some of these, I'll characterize them as philosophical points, but I can see where and I can see where he's going with them. So the latest post there is investing time, energy, and technology in developing a system or systems to foster and support healthy collective will to shift into will that shift into collective regenerative consciousness? Is that fundamentally needed? I garble your message, John. My apologies, but in a sense, it's a new way of thinking. In a way that a new way of collaborating to overcome some of this kind of traditional bureaucratic siloed and evasiveness in the population. Is that something that interests you or you align to, Tom?
It's not something I know anything about, to be honest. I'd be interested to know more, but I don't think I could comment at this stage. Yeah, it's not something I've looked at.
I mean, where I would take it, I don't know if John would agree, but writers like Timothy Morton point out that, in a sense, attitudinal change, empathetic change, has to be attitudinal rather than policy. In a sense, people respond to their local woodland or to animals more readily than they do to policy directives, for example.
Yeah, no, that makes sense.
Fall in love with the hedgerow.
Yeah, fall in love with the hedgerow, basically.
It might
fall in love with the hedgerow.
I don't know, but it might be something that gets picked up by that these sort of social tipping points that that Exeter are looking at.
Yeah, I think so. There might be ways of in a sense looking. I don't want to call measures, but looking for clues about sort of attitudinal horizons being reached, if I put it like that.
I mean, certainly there's lots going on to try and reach out to the general public. We talked about the national emergency briefing and the people's emergency briefings and so on. There are other things. I noticed a friend of mine come up on the chat, Anne, who runs things called carbon literacy, carbon literacy training. So you can have Anne or another expert come into your company and spend a day taking your employees, your engineers, your salespeople, whoever, through a day of carbon literacy training. And I've sat in on one of Anne's sessions, and it's brilliant. It's very, very well worthwhile. So that would be another way, particularly because it's you get people at home through the national emergency briefing type thing. And then if you can get people sort of talking about it at work and getting companies to change their policies or procedures or so on, then that's very worthwhile.
Methinks there's an educational emergency in all this as well, right from 5 years upwards in the schools that we have, and also in the universities and the postdoc, etc., education that we give people. Because we focus very much on the tangible aspects of the numeracy of things and the connection to the economics of things, but not to the humanity and how we affect each other through the choices that we make.
Yeah.
So there's an education emergency, and I believe it starts in kindergarten.
Mm-hmm.
Yeah, I found it really, really interesting, actually. Sorry. I just something.
Yeah. Go on. It's all right. We can turn off the recording now. By the way, Peter.
Just something interesting about what you said with like economics. Economics, I'm sure you all are aware, is actually split into what's known as orthodox and unorthodox economics, or heterodox economics, and that in and of itself is interesting because nothing about it says that one of them or the other is empirically better than the other one, and yet they're both separated, and orthodox is what's actually taught in schools and taught in universities.